Okay, so we're given H3C, parentheses 2, SO. We start with our central atom, S, which is attached to an oxygen, and two CH3s. So you have CH3, CH3, and an oxygen. So right now we need to add the lone pairs on each atom. Oxygen wants 8 in its valence shell, so we add 1, 2, 3, 4, 5, 6, and this bond counts as 2. Sulfur wants 8 as well, so we have 2, 4, 6, so we need to add a lone pair, 8. The CH3s already have 8 in their shell because they're attached to 3 hydrogens and then attached to the sulfur. So what's next are the formal charges. According to the octet rule, oxygen can only have 6 in its octet. Right now, it has 1, 2, 3, 4, 5, 6, 7. Each lone pair counts as 1, and each bond counts as 1. That would put it at a negative charge. It needs to go down. Sulfur has 1, 2, 3, 4, 5. However, sulfur is special, and it wants to hold 6. So it needs to go up 1, putting it at a positive charge.
So here we're given H2C and N. You'd start with your central atom being N. And around the end, you'd have bonded to the other end, which is here, and then the C is here, and that has 2 hydrogens coming off of it. Between here, you would have another bond, and here, you'd also have another bond. Now, because nitrogen can only hold 5, this would have 1, 2, 3, 4, 5, 6, making it negative. And this already has 4. This counts as 1, 2, 3, and 4, so it needs 1 more, obviously, to add your hydrogens.
Okay, so we're given H3C, C, triple bonded to NO. We start writing our C's. C bonded to C. Up here it told us there's a triple bond from C to N, so we go ahead and write the N, or the triple bond, to the N. And then we just expand from there. This C, which is right here, is connected to 3 hydrogens. So draw your hydrogens, and then the N is connected to another oxygen. Next, what we would want to do is fill the valence electrons. Each, unless they're special, wants 8. Carbon has 2, 4, 6, 8, so it's full. This carbon has 2, 4, 6, 8, it's full. This nitrogen has 2, 4, 6, 8. However, we have to check formal charges. Nitrogen, according to the octet rule, will have a formal charge of 5. Right now it has 1, 2, 3, 4, so it needs to go up 1, it's positive. Oxygen has 1, 2, 3, 4, 5, 6, 7. It needs to go down 1, it's negative.
So we're given N is triple bonded to C, which is bonded to a CH2 with a negative charge on the C. So in this problem, we're going to want to make a resonance structure. So here, we'll want to get rid of this negative charge on the C. To do that, we will move 1 bond from here to here, making that N double bonded to C, double bonded to C, H2. Now this gets rid of the negative charge, because C is now full. However, we just removed electrons from nitrogen. Nitrogen was already full. It had 1, 2, 3, 4, 5. However, we took away 1. So we put 1, 2, 3, 4, 5, 6. That makes nitrogen negative.
So here, this is what we're given, and we're asked to find a resonance structure. First thing we want to do is get rid of the negative charge. So how we're going to do that is we're going to move this double bond to this bond right here. So we redraw that, and we have this with a double bond here. You keep the H2C and the CH3 on each end. So when we look at this carbon right here, if you were to completely draw it out, you would have C double bonded to whatever is here and 2 H's. Remember your octet rule, carbon can only have 4 because it only brings to the table 4. Right here, it has 1, 2, 3, 4. So that means it will not have a charge. So this carbon is taken care of. But we need to pay special attention to this carbon right here because we moved the double bond. So if we were to draw this out, this has a hydrogen. So it would look something like this. Remember your octet rule? Carbon can have 4, but it still needs to fill its valence. So right now it has 2, 4, 6, so we add a pair of electrons to make it 2, 4, 6, 8. Now we have to think about formal charges with the octet rule. Counting your formal charges, you have 1, 2, 3, 4, 5. Since carbon can only have 4, it needs to go down 1. So we have the lone pairs here that we added over to this carbon, and that makes this carbon negative, and that would be your resonance structure.
In this problem, we are going to draw a resonance structure. To do that, we're going to need to get rid of this negative charge or move it somewhere else. So first, we would move this bond, moving it right here to be bonded to the O, visibly seen like this. So first, let's draw out our hexagon. All right, then we draw out our double bond to the O and give it its lone pairs. Now, oxygen now has 1, 2, 3, 4, 5, 6, which is what it wants. However, because we moved this double bond away, that makes this carbon right here negative, and it leaves it with a lone pair, just like that.
So in this problem, it's asking us to draw the structure after the mechanism arrows happen. So, how to start this problem? We start with our central carbon, C, which is bonded to H, nothing changes there. But if you look here, this bond is attaching to the H. So, we have it bonded to the C. This is now a double bond. And you have 2 H's. This H came from this H right here, which is bonded now to this C, which is right here. So, the bromine, the reason we don't draw the bromine within this structure is because the bond here is breaking. So the bromine gets essentially left behind. So you would draw your structure like this and then have bromine with its lone pairs and a negative charge. Now, we have to do the charge on this carbon right here. It has 2, 4, 6, so it needs 8. It'll have a lone pair, 1, 2, 3, 4, 5. That's too many, needs to go down. Oh, no, it's a positive charge. Sorry. So you have 1, 2, 3. It needs to go up 1. It's a positive. You don't have a lone pair on this one because you started with a fixed number of valence electrons, and adding a lone pair to this carbon would push it over.
In this problem, we are wanting to draw the products that are formed after the mechanism arrows have been completed. So first, you would start with this mechanism arrow first and do that. So that would be this electron pair connects to the H. So this would be OH in the end. It would be written out as H3C bonded to a C right here, but we won't draw that, to a CH3, double bonded now to OH. Now this O here, it just gains a new bond with H. So now it's given, it still has its other lone pair of electrons, and it makes it positive. Now, this last pair, last area here, the electrons, the pair here now goes to the oxygen. So this is seen as sulfur in the middle as your central atom, bonded to the HO up here, also double bonded to S, to O with its lone pairs. Double bonded to O.
Too many O's.
And bonded to O again. However, this O is different. This O is different than this O because this O now has this pair that just came to it. So this has a new set of electron pairs. That means it makes it negative.
Okay, so this question is asking which reactant is missing. Well, what the reactant is that is missing. So this is your first reactant, this is the second one you're missing, and these are your products. Easiest way to do this problem is to keep inventory of how many elements you have. So we have a carbon, hydrogen, oxygen, and over here we have a sodium, a nitrogen, and I think that's it. So just draw these on the other side. CHO, Na, and nitrogen. So then we just count how many we have. So 1, that's just 1 carbon. We have 4 hydrogens, 3 here, 1 oxygen, and we don't have any sodium or any nitrogens. So carbons over here, we have 1 carbon, but pay attention to the hydrogens. We have 3 here, and we have 3 down here. So that's actually 6 hydrogens. For oxygens, we only have the 1. Sodium, we only have the 1. And for nitrogen, we only have the 1. So we look and see what we're missing. We have 1 carbon on this side, 1 on this side. So that's fine. For hydrogens, we have 4 on this side and 6 on this side, so we're missing 2 hydrogens somewhere. We have 1 oxygen, that's good. We need a sodium over here and a nitrogen over here. So you'd have NaNH2. Is that right?
So in this problem, we are having to figure out what is missing in the reactant side. Reactant side being over here. The product side is this. So the easiest way of going about this, as stated before, is to count how many carbons you have, how many hydrogens, how many oxygens, and over here we have sodium. So how many sodium? On carbon, we have 1, 2, 3, 4, 5, and 6. Hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 hydrogens. We have 1 oxygen. We have no sodium. On this side, we have CHO, sodium. We have 1, 2, 3, 4, 5, 6 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. However, here, this is different. It's a negative. So this would only have 1 hydrogen on it, making it having 11 hydrogens on this side. It has 1 O and 1 sodium. So the difference between these carbons, we have 6. We have 6. We are missing 1 H. We are missing 1 Na. So it would be NaH.